Imagine drifting through a darkness so complete it feels untouched, unshaken, almost impossibly calm. Not the familiar night sky, strewn with stars, planets, and galaxies, but something older, deeper, a darkness from before structure existed. A darkness from when the universe was still too young to have anything to shine. And then, a glow. Faint, gentle, evenly spread across the whole sky. A whisper of light stretched thin by billions of years of cosmic expansion, yet still here, humming softly in every direction. This is the cosmic microwave background, the oldest light we can ever see. A fossil photograph of the universe as it looked roughly 380,000 years after the Big Bang, a moment when matter finally cooled enough for electrons and protons to combine and form neutral atoms, allowing light to travel freely for the first time. Before this moment, the universe was an opaque plasma, hot, dense, bright, and turbulent. Photons bounced around endlessly, unable to travel without slamming into charged particles. But as the cosmos expanded and cooled, dropping to roughly 3,000 Kelvin, about 2,700 degrees Celsius and 4,900 degrees Fahrenheit, the fog lifted, light broke free. It began a journey outward that would last more than 13.8 billion years, eventually stretched into microwaves as space continued to grow around it. Now it reaches us as a faint glow, just 2.725 Kelvin above absolute zero, not much warmer than nothing, and yet it fills the present-day universe like a quiet, uniform memory. Imagine floating inside it. No stars, no galaxies, no planetary silhouettes, no bright clusters, nothing to orient yourself. Only this delicate wash of ancient radiation, smooth as a still lake at dawn. Calling it a background barely captures what it truly is. The cosmic microwave background is the universe's autobiography, written in temperature ripples so tiny, millionths of a degree, that they nearly vanish into the noise. But they don't. Those tiny fluctuations are fingerprints from the primordial universe. They come from quantum variations stretched to cosmic scales during a flash of inflation. They record sound waves moving through the early plasma. They trace the distribution of matter before galaxies ever formed. They are the seeds from which everything, every star, every planet, every living thing would eventually emerge. When spacecraft like COBE in 1992, wmap in 2003, and Planck in 2009 mapped this ancient radiation with increasing precision, the result was astonishing. For the first time, humanity could look directly at the texture of the infant universe itself. What they found appeared mostly smooth, astonishingly smooth, confirming that the early cosmos was remarkably uniform. But it wasn't perfectly uniform. Scattered across the map were patches slightly warmer or cooler than the average tiny variations that cosmologists expected. They were the evidence of early density fluctuations, the imprints of primordial sound waves, the subtle record of gravity shaping the universe even in its earliest moments. And then something stranger appeared. A region larger than most, quieter than most, colder than it had any right to be. A vast patch of sky in the direction of the constellation Eridanus. This odd region would come to be known simply as the cold spot. Picture the ancient microwave sea again. Imagine its faint, speckled pattern of subtle, warm and cool tones. Now imagine noticing a depression, an area where the temperature dips by about 70 microkelvin relative to its surroundings. A tiny difference in absolute terms, but cosmically meaningful. That depth, spread over such a wide region, hundreds of millions of light years, was statistically unusual. Too unusual for cosmologists to ignore. When wmap first revealed it in 2004, researchers double-checked their calibrations. They re-examined the sky cuts. They debated whether it might be an artifact, a processing error, a leftover systematic. But then Planck, with its higher sensitivity and finer resolution, confirmed it. Whatever the cold spot was, it wasn't a mistake. It was real, a cool, coherent anomaly imprinted on the universe's earliest detectable light. Imagine drifting toward it now through the pale microwave haze. All around you, the ancient glow is almost perfectly smooth, but in the distance you sense a soft dip in that smoothness, like noticing a slight hollow in an otherwise even sea. Not a sudden plunge or dramatic abyss, more like a gentle, persistent lowering of the cosmic temperature, as though the early universe exhaled a little differently in that spot. Most fluctuations in the cosmic microwave background follow predictable statistical patterns. They arise from random processes in the early plasma, shaped by inflation and acoustic oscillations. But this region, this one deviates slightly more than expected, enough to make cosmologists wonder whether it represents a rare coincidence or the signature of something deeper. Is it an enormous supervoid in the present-day universe pulling energy from passing photons? An ancient cosmic texture left over from symmetry breaking in the early universe? A relic of inflation? Or even the faint bruising from a collision between our universe and another? Nothing in this oldest light screams for attention. Everything whispers instead. The cold spot is the softest whisper of all, a muted dip in a sea of uniform glow, subtle, persistent, and waiting to be understood. As you remain suspended in this ancient radiation, the cold spot feels like a quiet question etched into the afterglow of creation. A small imperfection in an otherwise symmetrical sky. A reminder that the cosmos, even in its earliest moments, held mysteries that still ripple through time. A silence inside the oldest light. Slightly colder than it should be. A cosmic anomaly that has followed us across billions of years. Awaiting explanation, the ancient glow surrounding you begins to draw back as though the immersion is slowly giving way to clarity. The vast, featureless sea of faint radiation becomes easier to understand, easier to define. You start to feel the temperature of the universe's past settling around you. In this gentler turn of the narrative, where the imagination softens and science begins to speak more plainly, this is usually where I pause for a moment and say, before we go deeper, if you enjoy exploring the quiet wonders of the cosmos like this, consider subscribing and leaving a comment with where you're listening from and what time it is there. It helps this channel grow, and it keeps these journeys alive. Now, with the quiet invitation spoken, the scene opens wider. The faint afterglow becomes something more than a visual. It becomes a story written across all of space-time. To understand what the cosmic microwave background truly is, you have to imagine a universe that was once blindingly bright. Not filled with stars, those didn't exist yet, but filled with light trapped inside a dense, turbulent plasma. In the first few 100,000 years after the Big Bang, the cosmos was a roaring ocean of energy. Temperatures soared to levels that make even the cores of stars look cool. Photons bounced endlessly between free electrons and protons, unable to travel more than a few centimeters before scattering again. This early universe was incredibly small by today's standards, but impossibly vast in energy. If you stood in that epoch, which you could not, because atoms didn't exist, and neither would you, the light would have been everywhere, overwhelming, constantly interacting with matter. The cosmos was opaque because no photon could travel uninterrupted. Every direction was a wall of plasma. And then, around 380,000 years after the Big Bang, everything changed. The temperature of the universe dropped to about 3,000 Kelvin, around 2,700 degrees Celsius, 4,900 degrees Fahrenheit. This was cool enough for electrons and protons to finally settle into stable orbits, forming the first neutral hydrogen atoms. With electrons no longer flying freely, photons suddenly had room to move. The fog lifted, the universe became transparent, and light escaped. That light is what we now call the cosmic microwave background, or CMB. These primordial photons have been travelling ever since, stretched by the expansion of space itself. What began as visible and infrared light has now been pulled into the microwave range, wavelengths millimeters long, low energy, but still carrying the imprint of the universe's earliest conditions. When we detect the CMB today, we're not seeing something that happened recently. We are observing the oldest snapshot possible, the moment the universe went from opaque to transparent, a cosmic horizon. Beyond that surface, we cannot see, not because there is nothing there, but because light from earlier times has never had the chance to reach us. In that sense, the CMB is the universe's own photograph of its childhood, a frozen echo of the recombination era, preserved perfectly for nearly 14 billion years. But why is it so uniform? Why is it almost the same temperature in every direction? This is where the universe reveals one of its most astonishing chapters. Inflation. Just a fraction of a second after the Big Bang, far sooner than recombination, the universe underwent a period of exponential expansion. Tiny quantum fluctuations were stretched across astronomical distances. Regions that were once in close thermal contact suddenly became separated by billions of light years. Inflation smoothed the universe, ironing out any large-scale temperature differences, yet preserving tiny ripples. Those same ripples we now see as slight variations, warmer and cooler patches, in the CMB map. Without inflation, the CMB's uniformity would be impossible to explain. Regions of the sky too far apart to have ever exchanged information somehow share the same temperature. Inflation provides the missing link. But uniform doesn't mean perfectly smooth. Those tiny temperature variations, micro-Kelvin differences, are immensely important. They reveal the primordial density fluctuations that would later become galaxies, clusters, and cosmic filaments. They are the seeds from which cosmic structure grew. The first time humanity saw this ancient structure was in 1992, when COBE, the Cosmic Background Explorer, released its data. Until then, we knew the CMB existed. Arno Penzias and Robert Wilson accidentally discovered it in 1964 while investigating noise in a microwave antenna in New Jersey, but we had never seen its subtle fluctuations. COBE's results were astonishing. The map was rough and speckled, not the perfect smoothness many had assumed. Stephen Hawking famously said it was the greatest discovery of the century, perhaps of all time, because it showed the primordial seeds of structure, visible evidence of the early universe's imperfections. But COBE's resolution was coarse. It could see the general shape, not the fine details. The next step came in 2001 with wmap, the Wilkinson Microwave Anisotropy Probe. wmap sharpened the view dramatically. It mapped the sky with far greater clarity, revealing intricate patterns of warm and cool spots. These ripples aligned beautifully with theoretical predictions from inflation and the standard cosmological model. And then, in 2009, the Planck satellite elevated the field to a new level of precision. Planck observed the CMB with exquisite accuracy, unveiling not only the temperature variations, but also the polarization of the radiation, clues about how light scattered during recombination, and how gravitational waves from inflation might have left their signature. Together, COBE, wmap, and Planck form a timeline of discovery. COBE proved the fluctuations existed. wmap mapped them in detail. Planck refined the picture to near perfection. The cosmological parameters we rely on today, like the age of the universe, the density of dark matter, and the amplitude of primordial fluctuations, are measured with extraordinary precision thanks to these missions. And embedded in these maps, within the sprawling structure of tiny deviations, lies the cold spot, a region that doesn't behave quite like the rest, slightly deeper, slightly larger, slightly stranger. To understand the CMB is to understand the physical conditions that created it. It is not merely an image, it is data encoded in temperature, polarization, and angular scales. It tells us that the universe is flat to remarkable precision. It informs us about the composition of the cosmos, roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. It constrains inflation models, dark matter properties, and even the neutrino background. Every bump and dip in the CMB map is a clue. Every fluctuation is a fossil. Every microkelvin deviation is a whisper from the early cosmos. The cold spot is one of those deviations, but unlike most, it stands out sharply enough to stir debate. But that story comes a little later. For now, imagine the CMB not as a flat picture, but as a spherical shell surrounding us, the edge of the observable universe. Every direction you look, you are seeing photons from the same event, the universe becoming transparent. Every square centimetre of the sky carries this faint glow, unchanged except for the cosmic expansion that stretched its wavelength. It is astonishing to think that the photons hitting your microwave antenna today started their journey long before the Milky Way existed, before stars, before galaxies, before any structure at all. They are messengers from a time when nothing recognizable in today's universe had yet taken shape. And among these ancient messengers are the photons from the cold spot, slightly cooler, slightly dimmer, slightly different. Not yet explained, but undeniably real. A faint suggestion that something unusual happened in that region, or that something unusual lies between us and that region, or perhaps nothing unusual at all, just cosmic randomness creating a rare fluctuation. Just like the CMB itself, the mystery deepens as we study it. The more precisely we map it, the more questions it raises. And among all the questions, the cold spot remains one of the most compelling. The cosmic microwave background may appear calm at first glance, a faint and uniform glow stretched across the entire sky. But as scientists began to study it more deeply, they realized that the CMB is not a perfect blanket of ancient radiation. It is textured, subtle, speckled with countless tiny variations in temperature, each one carrying information from the early cosmos. Most of these differences are astonishingly small, only a few microkelvin above or below the average temperature of 2.725 Kelvin. A microkelvin is just 1/1,000,000th of a degree. Even for cosmology, that is finely measured. Yet those microscopic fluctuations are precisely what reveal the story of the young universe. Without them, galaxies would never have formed. Without them, the universe would still be a featureless fog of matter and radiation. To understand these variations, it helps to imagine the early universe not as silent or still, but as a churning ocean of sound, an immense, dense plasma where matter and radiation were tightly coupled, pushing and pulling against one another in enormous waves. These waves were real, pressure waves or acoustic oscillations rippling through the primordial plasma. In that early, opaque epoch, photons constantly collided with charged particles, and gravity acted to pull matter together. Radiation pressure pushed outward, creating a tug-of-war. This constant struggle produced compressions and rarefactions, regions where the density was slightly higher or slightly lower. Higher density regions trapped photons and heated up. Lower density regions allowed photons to escape more easily and cooled down. The result was a universe full of sound waves, oscillating at scales far beyond anything we could ever hear. When you see the mottled map of the CMB, those warm and cool spots are the frozen imprints of these ancient oscillations. Where the plasma was slightly compressed, the temperature appears a bit hotter. Where it was slightly rarefied, the temperature appears a bit cooler. These variations directly reflect density differences in the early cosmos. When the universe finally cooled enough for neutral atoms to form, when recombination happened, the photons that had been bouncing around inside this turbulent plasma suddenly streamed outward, carrying with them the imprint of those oscillations. This is why the CMB map is not uniform at the microkelvin level. It encodes the structure of those primordial sound waves. The distribution of these fluctuations isn't random noise. They follow a pattern that aligns beautifully with the mathematics of inflation and the physics of the early universe. Cosmologists often describe the CMB fluctuations as a Gaussian random field, which means the overall pattern has predictable statistical properties, even though each exact spot is unpredictable. On a full-sky CMB map, warm spots appear in yellow or red, representing slightly higher temperatures, while cool spots appear in blue. These features correspond to tiny density differences of roughly 1 part in 100,000, and yet they would eventually dictate the entire structure of the cosmos. Higher density regions became the seeds for galaxies. Lower density regions became the voids between cosmic structures. The large-scale distribution of matter today traces directly back to these early fluctuations. Mapping these fluctuations required extraordinary precision. When COBE first revealed the rough structure of the CMB, it was like seeing the universe's baby picture for the very first time. But the details were blurred. wmap sharpened that image dramatically, allowing scientists to measure the temperature of the CMB to within a few microkelvin. Suddenly, the acoustic peaks in the power spectrum, the signature of those primordial sound waves, became visible and unmistakable. With Planck, launched in 2009, the view became even sharper. Planck's instruments measured tiny temperature variations with incredible fidelity, mapping the sky with resolution down to about 1/10 of a degree. The sky transformed from a grainy mosaic into a precise high-resolution diagram of the early universe, and with this clarity came surprises. Among the sea of fluctuations, most small, most expected, one feature drew attention. A region colder than the rest. Not slightly colder, not an ordinary cool patch. Something deeper, something larger, something that stubbornly refused to blend into the statistical background. This wasn't just one pixel or one small anomaly. It spanned a region of sky roughly 5 to 10 degrees across. An enormous area, considering the entire sky is about 41,000 square degrees. It appeared consistently in wmap's maps, and again with higher fidelity in Planck's. Scientists nicknamed it simply the cold spot. At first, cosmologists assumed that large cold patches were simply natural outcomes of randomness. After all, if you generate enough random variations, some will be larger than average. But the cold spot was too pronounced, too coherent, too deep in temperature compared to its surroundings. A typical fluctuation might be a few tens of microkelvin. The cold spot measured around 70 microkelvin below the mean. This depth alone wouldn't necessarily be concerning, but its scale, its sheer width, pushed it beyond what standard cosmological models predicted. The probability of such a feature occurring purely by chance is small. Not impossible, but low enough that it generated immediate interest. Mapping the cold spot in detail required careful analysis. Temperature maps alone aren't enough to understand an anomaly this large. One also needs to examine the statistical distribution of fluctuations. Typically, cosmologists compare real CMB data to thousands or even millions of simulated universes generated according to the parameters of the standard cosmological model. In these simulated universes, random fluctuations vary widely, yet very few of them include a region resembling the cold spot. This statistical tension is what drives the mystery. Not that the cold spot exists, but that it shouldn't be quite so cold or quite so wide if the universe obeys the simplest inflationary models. Something appears slightly off, slightly unexpected. Still, before leaping to exotic explanations, scientists had to make sure the anomaly wasn't coming from something mundane. Could dust in the Milky Way be creating a false cold patch? Perhaps an error in how foreground emissions were removed, or an artifact introduced by smoothing or processing the data. Each possibility was examined in detail. Foreground contamination was ruled out. The anomaly persists even in the cleanest data channels. Instrumental effects were ruled out. Both wmap and Planck saw the same structure, despite using different instruments and analysis techniques. Statistical misinterpretations were scrutinized, and while the probability remains low, it is not zero. After eliminating these possibilities, cosmologists were left with two broad explanations. Either the cold spot is as an extremely unlikely statistical fluctuation, or a sign of some physical mechanism not accounted for in the standard model. The latter option opens the door to some bold ideas, enormous cosmic voids, exotic topological defects, or even traces of a collision with another universe. But before venturing into those possibilities, it's important to understand exactly what the CMB fluctuations represent. The temperature variations across the sky correspond directly to density variations in the early universe. Warmer regions indicate slightly higher density and stronger gravitational potentials at the time of recombination. Cooler regions correspond to lower density. Over billions of years, these density differences would evolve into the cosmic web, the filaments, clusters, and voids that shape the large-scale structure of the cosmos today. If a patch of the CMB is unusually cold, it implies something peculiar about the density fluctuation that produced it. Maybe that region was less dense than expected. Maybe light traveling from that direction passed through an unusually underdense structure, a supervoid, that caused it to lose energy. Or maybe there was something even more fundamental happening at the moment when the universe became transparent. But the mapping itself is unambiguous. The cold spot is not a processing glitch, not an illusion, not a statistical mirage caused by a small sample size. It is a genuine temperature depression in the CMB map, consistently measured by multiple missions and confirmed with high statistical confidence. It was first recognized clearly in wmap's 2004 data release, standing out like a shadow in the early universe's glow. When Planck published its refined full-sky maps in 2013 and later updates, the cold spot was still there, sharper, better defined, but just as puzzling. The CMB map is like a fossil, and the cold spot is a strange indentation on that fossil, slightly deeper than it should be. Slightly larger than expected, slightly too persistent to dismiss. And as we continue peeling back the layers of this anomaly, the question becomes, what created this unusually cold region in the oldest light of the cosmos? When the first full-sky temperature maps from the Wilkinson Microwave Anisotropy Probe, better known as wmap, were released in 2004, cosmologists expected surprises. Anytime you measure the universe with better precision, the universe tends to offer something unexpected. But no one expected the cold spot. Not this feature, not this large, not this deep. MAP's mission was launched in 2001 with a bold objective: to produce a detailed, high-resolution map of the cosmic microwave background, improving on what the earlier COBE satellite had achieved. COBE's detections of large-scale temperature fluctuations in 1992 were groundbreaking, but the map lacked fine structure. It showed the universe's baby picture, but only in broad strokes, like an out-of-focus photograph. wmap was designed to fill in those details, revealing the acoustic patterns, temperature fluctuations, and primordial irregularities at much smaller angular scales. Over the next several years, wmap scanned the sky continuously, mapping temperature variations on scales as small as 0.2 degrees. It measured the CMB with exquisite accuracy, down to a few microkelvin. The mission's first data release in 2003 already hinted at something interesting, but it was the more complete 2004 release, the one containing the first full sky maps with improved processing, that caught everyone's attention. The cold spot appeared as a deep, coherent blue region stretching across a patch of sky in the constellation Eridanus, a region roughly 5 to 10 degrees wide, depending on how one defines its boundaries. It was not a vague anomaly. It had a defined centre, a gradient, and enough spatial coherence to stand apart from typical random fluctuations. Temperature depressions in the CMB are normal. Countless cold patches exist across the sky. Most are small, shallow, and statistically unremarkable. But the cold spot was different. Its central temperature was roughly 70 microkelvin below the average, a figure far deeper than one might expect from purely random fluctuations predicted by the standard cosmological model. Cosmologists immediately began to analyze the map. Was this an artifact? Was it caused by contamination from galactic dust, synchrotron radiation, or emission from other astrophysical sources? wmap's team had spent years developing algorithms to remove these foreground contributions. Even so, foregrounds can be tricky. They can hide, distort, or mimic signals. But the cold spot persisted no matter how the data were cleaned. Different frequency channels, each sensitive to different types of foreground contamination, showed the same feature. The region appeared in the Q-band, V-band, and W-band maps, even when conservative masks were applied to remove the Milky Way's dust and radio emissions. The anomaly remained. That alone was notable. Truly spurious features usually dissolve under such scrutiny. This one didn't. Statistical analysis made the situation even more interesting. Cosmologists simulated enormous ensembles of CMB maps based on the standard LCDM model, the model describing a universe of cold dark matter and dark energy, with inflation setting the initial conditions. In these simulated universes, temperature fluctuations appear randomly, following Gaussian statistics. Most fluctuations cluster around the average, some deviate more. A few deviate a lot, but across thousands upon thousands of simulated universes, very few contained a region quite like the cold spot. Estimates varied, but many studies converged on a similar result. The likelihood of such a feature appearing purely by chance was low. Some analyses placed the probability at around 1 to 2%, while others suggested it could be even lower, depending on which statistical methods were applied. Still, low probability is not impossibility. If you flip a coin 1,000,000 times, you will get some remarkable streaks. The universe, operating at unimaginable scale, can produce patterns that look meaningful even if they arise purely from randomness. So while the cold spot was notable, cosmologists remained cautious. It was too early to call it evidence of new physics. Even so, the cold spot's coherence raised eyebrows. Temperature depressions usually occur as part of a noisy landscape, blending and fading into surrounding fluctuations. But this region had a distinct shape, a central depression with a slightly warmer ring-like structure around it, followed by cooler edges. The gradient wasn't typical. It was too structured, too large in angular scale. The cold spot wasn't just cold, it had personality. As the years passed, the anomaly remained a topic of scientific curiosity. Papers were written. Graduate students sharpened their statistical skills on it. Entire conference sessions were devoted to understanding it. Then came Planck. Launched by the European Space Agency in 2009, the Planck satellite was designed to produce the most precise CMB map ever made. Its detectors had higher sensitivity and finer angular resolution than those on wmap. Where wmap observed at 5 frequency bands, Planck observed at 9, allowing unprecedented separation of foreground contamination from the genuine CMB signal. When Planck released its first major full-sky CMB map in 2013, cosmologists immediately looked toward the region where wmap had found its anomaly. If the cold spot persisted in Planck's data, the anomaly would graduate from curiosity to confirmed feature. And indeed, it was there, sharper, cleaner, just as cold, just as wide. Planck's data removed any lingering doubts about instrumental or processing errors. The anomaly survived every test: frequency channel separation, foreground subtraction, component analysis, and noise modelling. It appeared consistently in the 2013 map, and again in the higher precision 2015 and 2018 datasets. With each release, the cold spot's existence became more secure, even as its explanation remained elusive. Planck's enhanced precision also allowed cosmologists to analyse the cold spot's morphology in detail. They noticed something interesting. The region wasn't uniformly cold. Its internal structure had subtle patterns, radial temperature gradients, slight asymmetries that didn't match simple Gaussian predictions. These features made the anomaly even more intriguing, suggesting it might not have arisen entirely from random initial fluctuations. The cold spot stood out in another way as well. The CMB contains billions of pixels, little temperature values across the entire sphere of the sky. Among this sea of fluctuations, most pixels blend into the statistical background, but the cold spot's combination of size, depth, and shape landed it in the extreme tail of the distribution. In simpler terms, it was a rare outlier, not impossible, but rare enough that cosmologists kept returning to it, trying to understand what made it so exceptional. Not every anomaly merits this level of attention, but this one did, because it persisted under increasingly stringent measurements across multiple instruments, multiple cleaning methods, multiple analysis pipelines. And persistence is a powerful motivator in science. The cold spot wasn't the only anomaly in the CMB. There were others: the hemispherical power asymmetry, the alignment of the lowest multipoles, and certain large-angle correlations that seemed weaker than predicted. But the cold spot was the most visually striking and statistically persistent of them all. Its existence posed an uncomfortable question. Was the anomaly simply the tail end of cosmic randomness? Or was the CMB giving us a hint of something more exotic, something not accounted for in the standard inflationary model? Scientists proposed explanations ranging from the mundane to the extraordinary. Perhaps the cold spot was caused by a large void in the distribution of galaxies, an underdense region in the nearby universe that could cool CMB photons via the integrated Sachs-Wolf effect. Or maybe it was caused by a topological defect in the early universe, a cosmic texture left over from symmetry breaking. Or perhaps, more daringly, it was the signature of a cosmic bubble collision, a remnant of interaction with another universe during inflation. Each of these ideas would be explored in the years to come, but before any of that could be understood, the first step was accepting the anomaly's reality. wmap saw it. Planck confirmed it. And despite thousands of papers and simulations, the cold spot remained a stubborn presence in the CMB sky. Improbable, persistent, and undeniably real. A silent depression in the oldest light of the universe, standing out among billions of fluctuations like a quiet fingerprint from something unknown. The idea that the cold spot could simply be a random statistical fluke is not the most exciting explanation, but it remains one of the most scientifically responsible ones. Before invoking exotic physics, bubble universes, topological textures, or massive cosmic voids, cosmologists must first test whether the anomaly can be explained by the basic statistical nature of the cosmic microwave background itself. And understanding that requires stepping briefly into the strange but powerful world of Gaussian random fields. The CMB is not just a picture of the early universe, it is a statistical object with well-defined properties. According to the standard cosmological model, inflation produced tiny quantum fluctuations that were stretched to cosmic scales. These fluctuations evolved into the density variations that the CMB records. Importantly, inflation predicts that these fluctuations should follow a Gaussian random distribution. A Gaussian random field is not a complex idea at its core. Think of it as a landscape of hills and valleys whose heights follow a bell curve distribution. Most points lie close to the average value. Only a few lie very far above or below that average. The fluctuations we see in the CMB, those warm and cool patches, behave the same way. Most are mild, a few are a bit stronger, and extremely strong deviations are rare, but not forbidden. To determine whether a feature like the cold spot is truly unusual, cosmologists compare it not to a single model but to thousands, often millions, of simulated universes generated under the assumption that the cosmos behaves according to lambda, CDM, and inflation. Each simulated universe contains a CMB map with its own unique arrangement of hot and cold spots. These virtual skies are not identical to our real sky, but they follow the same fundamental statistical rules. They let scientists see how often something as cold and as large as the cold spot appears purely through chance. The answer is complicated because the probability depends on how exactly one defines the size, depth, and shape of the cold spot. But most analyses converge on a rough estimate. Something like this should appear in perhaps 1 to 2% of simulated universes. That is small, but not vanishingly small. It means that if one were to observe 100 random universes, 1 or 2 might display an anomaly resembling the cold spot. Rare events happen. Sometimes they happen exactly where we are looking. To get a sense of why this probability isn't unreasonable, imagine standing at a coastline covered with millions of pebbles. Most are ordinary, but a few, rare but inevitable, will be unusually smooth or strangely shaped. You might pick one up and marvel at its uniqueness, but uniqueness alone doesn't give it cosmic significance. It might still be just a pebble. The cold spot may simply be that pebble. In cosmology, an anomaly must be interpreted with caution. The discipline deals with huge data sets, complex correlations, and cosmic variance, the unavoidable fact that we observe only one universe and cannot rerun it to see how often a given feature appears. If one analyzes enough data, patterns can emerge that look remarkable but arise from random fluctuations. This is why cosmologists sometimes say the universe invites overinterpretation. It is easy to find faces in clouds when the clouds extend across the entire sky. The definition of an anomaly is itself not universal. An anomaly in cosmology is not simply something that looks unusual. It is something that stands out beyond what statistical models predict. But those models rely on assumptions. They involve smoothing scales, masks for foreground contamination, and decisions about which multipoles to consider. Varying any of these inputs can slightly change the anomaly's perceived significance. For example, some analyses find that the cold spot's probability is closer to 1%. Others find it might be as high as 5%. Still others suggest that when you consider multiple anomalies together, the so-called look elsewhere effect, the cold spot becomes less surprising. After all, if one scans enough features, one will eventually find something strange. The look elsewhere effect is especially important. It describes the fact that if you search for anomalies over the entire CMB sky, you cannot treat each anomaly as an independent event. You have already looked everywhere. Any particularly extreme feature becomes less significant because it was discovered among a vast field of possibilities. This effect is not a trick. It is a fundamental part of statistics. Without it, even ordinary fluctuations can masquerade as surprising. Some cosmologists argue that the cold spot loses much of its statistical tension when the look elsewhere effect is properly accounted for. In this view, the anomaly is not a sign of new physics, but a predictable outcome of random fields. Low probability, but not excessively so. Another argument for the statistical fluke interpretation comes from the shape of the cold spot. Although the central depression is unusually deep, the surrounding regions are not as anomalous. In a truly exotic explanation, one might expect the structure to display more distinctive properties, sharper edges, unusual gradients, or a more dramatic geometry. But instead, much of the cold spot's surroundings are consistent with ordinary fluctuations. Only the central core deviates strongly, and even that deviation fits within the extreme tail of Gaussian predictions. Planck's 2013 and 2018 data releases complicated the picture but did not overturn the statistical interpretation. Planck's improved resolution and frequency coverage confirmed the cold spot's existence, but also reaffirmed that Gaussian random fields still provide an excellent overall fit to the CMB sky. The cold spot stands out, but not enough to break the model. In fact, one of Planck's most important conclusions was that the CMB is statistically consistent with the predictions of LCDM and inflation. All anomalies, including the cold spot, lie near the boundary of what the model predicts, but not beyond it. Even if the cold spot were the rarest fluctuation in the sky, that alone does not prove it requires new physics. Some cosmologists take this position very strongly. They argue that searching for exotic explanations is premature. if not unnecessary. In their view, the cold spot is an expected occasional extreme. An outlier, yes, but an acceptable one. They draw comparisons to extreme events in other fields. For instance, in a large sample of random noise, one will inevitably find an unusually high peak or a deep trough. If you generate 1 billion numbers from a normal distribution, the largest deviation might be 5 or 6 standard deviations from the mean. That doesn't mean the process is non-random. It simply means you looked at a lot of data. The CMB contains billions of pixels. Even though they are not fully independent, the number of potential features is enormous. The cold spot may simply be the largest expected deviation in that vast data set. This argument is not appealing to those who prefer dramatic explanations, but it is powerful in its simplicity. It does not require new forms of matter, higher dimensional collisions, or exotic symmetry-breaking events. It does not require rewriting the early universe or adding extra parameters to inflation. It merely requires accepting that even the most uniform statistical processes produce outliers. Some cosmologists even argue that the fascination with the cold spot reflects a human tendency to seek meaning in noise. The CMB is one of the richest data sets in science. It is almost impossible not to find something intriguing within it. But intrigue alone does not guarantee physical significance. The cold spot could be nothing more than a statistical outlier, that strangely shaped pebble among millions of ordinary ones. The fact that it persists across different missions does not contradict its randomness. Gaussian random fields are robust, and their outliers are robust too. A rare fluctuation does not fade when observed more clearly. Still, even if the cold spot is just a random dip, it remains scientifically valuable. It reminds cosmologists that randomness is not monotony. It highlights the importance of statistical understanding in interpreting cosmic data, and it ensures that analyses remain grounded, resisting the urge to leap immediately to exotic conclusions. And yet, as some scientists have pointed out, the cold spot's depth and scale still feel a little too conspicuous. Even if the statistical explanation is adequate, it does not diminish the curiosity the anomaly inspires. For others, the anomaly's persistence nudges them to wonder whether something more might be at play. The statistical fluke hypothesis is the most conservative explanation. It is also the simplest. It requires no new physics, no vast structures in the nearby universe, no collisions with other cosmic regions. It allows the cold spot to be interesting but not revolutionary. Perhaps it is exactly that, a meaningful reminder that even the oldest light in the universe carries traces of randomness. Or perhaps it is something more. But before exploring more exotic explanations, one must consider the next possibility, that the cold spot could be the imprint of an immense structure lying between us and the surface of last scattering, a supervoid so large that it cools passing photons. The search for a physical explanation behind the cold spot naturally turned toward the universe's large-scale structures. Among the cosmic web's tapestry of filaments, clusters and voids, certain regions appear profoundly empty, expanses containing far fewer galaxies than average. These voids, while vast, are not unusual in themselves. They form naturally as gravity pulls matter into dense filaments and leaves behind underdense bubbles. But one particular void drew immediate attention, the Eridanus supervoid, situated in the same direction as the cold spot. If any structure could influence the CMB on such a grand scale, it would be something like this. The Eridanus region had already been noted for its lack of galaxies as early sky surveys expanded. Observations from the SDSS, Sloan Digital Sky Survey, and other galaxy catalogues revealed that, compared to typical cosmic voids, which might stretch tens of millions of light-years across, the region near the cold spot seemed unusually extended. By some estimates, depending on the definition and depth threshold, the Eridanus supervoid spans nearly 1 to 1.8 billion light-years in diameter. That makes it one of the largest underdensities ever identified, dwarfing more familiar voids in the cosmic web. Its structure, however, is not a simple spherical cavity. The Eridanus supervoid is more like a chain of connected voids, a complex and irregular underdense region stretched along our line of sight. The density contrast, how empty it is compared to the average cosmic matter distribution, remains modest. It is not a perfect vacuum. It contains galaxies, but fewer than average. Some analyses suggest a density deficit of around 20 to 30%, while others, depending on methodology, find slightly deeper deficits. These numbers matter because the ability of any void to affect CMB photons depends critically on its depth and extent. In an evolving universe dominated by dark energy, voids do not remain static. They grow as matter flows outward toward denser regions. As they expand, the gravitational potential within them changes over time. This is where the integrated Sachs-Wolf effect, or ISW effect, becomes essential. It describes how photons traversing changing gravitational potentials gain or lose energy. When a photon enters a void, it falls into a shallower gravitational well compared to a dense region. As it climbs back out, the potential has changed slightly. In a dark, energy-dominated universe, voids become less deep over time. Because of this, the photon may not fully regain the energy it lost falling in. The result is a tiny net cooling of the photon. This effect is extremely faint, but large voids can imprint detectable signatures on the CMB. Thus, the basic idea emerged. Perhaps the cold spot was caused not by an intrinsic temperature fluctuation imprinted at recombination, but by photons losing energy as they passed through the Eridanus supervoid on their journey to us. The logic was elegant. It relied on known physics, gravitational redshift, cosmic expansion, and the ISW effect. It did not require exotic scenarios. If the void were big enough and deep enough, it could create a measurable cooling. Perhaps not the entire cold spot, but at least a significant portion of it. Early studies seemed promising. Observations from galaxy catalogues indicated a substantial underdensity along the line of sight to the cold spot, and preliminary modelling suggested that the ISW effect from such a void could indeed produce a cold region in the CMB. This sparked excitement. The anomaly might finally have a conventional explanation. But the enthusiasm faded as more precise analyses were conducted. As cosmologists modelled the void more carefully, they found that voids, even large ones like Eridanus, could not by themselves produce a temperature depression as deep as the cold spot. A typical ISW temperature shift from a void of this size and depth might be on the order of 20 to 30 microkelvin, perhaps a bit more with optimistic assumptions. But the cold spot sits around 70 microkelvin below average. That discrepancy is not small. It is significant enough to strain the void hypothesis. One may attempt to stack voids or propose a filament of connected underdensities along the line of sight. This helps slightly. The Eridanus region indeed appears to contain multiple underdense zones arranged in a kind of layered structure, but even when combining the contributions of these segments, the total ISW effect still falls short. As the models became more detailed, it became clear that producing the observed depth of the cold spot using voids alone would require an underdensity far deeper than what galaxy surveys reveal. Some researchers proposed that the Eridanus supervoid might have unusual geometry, a kind of elongated or compensated void whose shape enhances the ISW effect. Others suggested that perhaps the void is actually deeper than observed because galaxy catalogues miss low-luminosity galaxies or because photometric redshift uncertainties smear structures. But again, improved data from surveys and better void reconstructions did not support a sufficiently deep deficit. The universe simply does not appear empty enough in that direction to explain the anomaly through the ISW effect alone. This does not rule out the void's involvement. Many cosmologists believe the Eridanus supervoid contributes part of the signature. Its size and orientation make it difficult to ignore. It likely plays some role in cooling CMB photons travelling toward us, but the amount of cooling it produces cannot fully account for the cold spot's observed amplitude. The void hypothesis, in its simplest form, explains the anomaly only partially. To understand why, it helps to consider how cosmic structures evolve. After recombination, matter slowly fell into gravitational wells created by the primordial density fluctuations. Dense regions grew denser as they accumulated matter, underdense regions grew emptier. The cosmic web, filaments, clusters, and voids emerged from these processes, but even the largest voids are not deep enough to drastically distort the CMB. The universe's matter distribution is simply not extreme enough for voids alone to carve out temperature dips of the cold spot's magnitude. The ISW effect, while conceptually straightforward, is inherently subtle. It becomes noticeable only because dark energy accelerates cosmic expansion, causing gravitational potentials to evolve. In a universe without dark energy, voids would not imprint such effects. But even in our accelerating universe, the effect is weak. Individual voids often produce temperature shifts of only a few microkelvin. Only the largest voids, on the scale of several hundred million light-years, can generate shifts near 20 microkelvin or more. The Eridanus supervoid is undeniably large, but size is not everything. Depth matters, and the void does not appear to be deep enough. This tension between expectation and observation is what forces researchers to consider alternative explanations. The void hypothesis is attractive because it remains within the framework of standard cosmology. It invokes no new physics, no speculative inflationary events, no multiverse interactions. It simply says, here is a large underdensity that happens to lie between us and the surface of last scattering. Yet simplicity must bow to accuracy. As galaxy surveys improved, most notably through deeper optical and infrared observations, cosmologists were able to map the Eridanus region with increasing precision. They found that while the void is large, its overall density contrast does not reach the extreme levels needed to produce a 70 microkelvin dip. Even with generous assumptions, the models consistently underpredict the observed temperature depression by a factor of 2 or more. Attempts to salvage the idea by positing exotic forms of dark energy or modified gravity that amplify the ISW effect remain highly speculative. These theories often contradict constraints from Planck data or large-scale structure observations. Mainstream cosmology does not support such enhancements. Thus, the supervoid hypothesis does not fully solve the mystery. It provides a partial explanation, a contribution, not a cause. It suggests that some fraction of the cold spot's depth may arise from photons losing energy while traversing the Eridanus underdensity, but the remaining depth, the part that stretches the limits of Gaussian statistics, remains unexplained. The void is not irrelevant, it is simply insufficient. This realization leaves the cold spot suspended between two interpretations, one invoking chance, the other invoking something more unusual. The void softens the anomaly, making it less extreme statistically, but it does not make it disappear. It cannot erase the possibility that something else, something imprinted at recombination, or something from even earlier cosmic epochs, played a role. Silence resumes around the anomaly. The photons continue their ancient journey, and the supervoid stands not as a solution, but as a clue, one piece in a puzzle that refuses to yield fully to ordinary explanations. Dark energy, the mysterious component driving the accelerated expansion of the universe, naturally entered the conversation once the supervoid hypothesis proved insufficient. If ordinary gravitational potentials cannot fully account for the depth of the cold spot, perhaps the anomaly reflects something deeper about how space itself expands. The idea is tempting because the cold spot sits at a scale where cosmic expansion, gravitational wells, and dark energy all intertwine. But as alluring as these possibilities are, they carry limitations that keep them at the edges of mainstream cosmology. To explore these ideas, it helps to recall what dark energy is, or rather, what we think it is. Observationally, dark energy reveals itself through the accelerating expansion of the universe. It behaves as a form of negative pressure permeating space, counteracting gravity on cosmological scales. In the lambda CDM model, the simplest explanation, dark energy is treated as a cosmological constant lambda, a uniform, unchanging energy density associated with empty space. But the cold spot provoked questions about whether dark energy might have spatial variations or dynamic behavior capable of amplifying the integrated Sachs-Wolf ISW effect beyond what simple models predict. If dark energy varies across space or evolves in a way that modifies gravitational potentials more dramatically than expected, then CMB photons could undergo stronger energy shifts when passing through certain regions. This line of thought is not standard cosmology, but it is mathematically plausible. The ISW effect is central here. When a photon crosses a gravitational well, it first gains energy falling in, then loses energy climbing out. In a universe dominated by matter alone, these energy changes cancel out perfectly. But in an accelerating universe, gravitational wells gradually fade in strength over time. As a result, photons lose slightly more energy climbing out than they gained falling in. This net loss cools the photon. Modified dark energy models sometimes attempt to magnify this effect. If dark energy were not uniform, if its density varied from place to place, then the rate at which gravitational potentials decay could differ across the sky. A region with slightly higher dark energy density might cause gravitational potentials to shrink more rapidly, enhancing the cooling effect. The cold spot's direction might coincide with such a region. In this scenario, the cold spot is not caused directly by a void, but by spatial variation in the underlying dark energy field. The void simply happens to sit where dark energy configuration enhances the ISW effect. Another possibility arises from models where dark energy interacts with dark matter. These coupled dark sector models propose that dark energy is not a passive background field, but a dynamic entity capable of transferring energy to or from dark matter. If such interactions were spatially dependent, they might create regions where gravitational potentials decay at different rates, influencing CMB photons more strongly. A third class of theories involves modifications to gravity itself. Instead of altering dark energy, these frameworks change the gravitational law on large scales. General relativity has passed countless tests, but mostly within the solar system or on astrophysical scales. At cosmological distances, hundreds of millions or billions of light years, it remains possible that gravity behaves differently. Modified gravity theories such as FR gravity or brane world models predict altered growth rates for cosmic structures. In these scenarios, voids might produce stronger ISW signals than standard physics predicts. If the cold spot aligned with a region where modified gravity effects are amplified, that might account for the discrepancy between observed and expected temperature depressions. Another intriguing possibility arises from dynamical dark energy, or quintessence, in which dark energy is treated as a scalar field that changes over time. Scalar fields can vary across space as well. If the cold spot intersects a region where the quintessence field differs from the cosmic average, photons passing through it could experience altered gravitational histories. In some inflation-inspired models, leftover large-scale perturbations in the dark energy field could produce giant hemispherical power asymmetries or localized temperature depressions. These would not be random fluctuations in the primordial plasma, but relics from energy fields that shaped inflation or its aftermath. Energy shifts in photons traveling through these modified gravitational landscapes would follow the same physical principle as the ISW effect, but magnified. A photon entering such a region might experience a gravitational potential that decays more quickly than normal. When climbing out, the potential might have weakened significantly, causing the photon to lose more energy than expected. Over a region spanning hundreds of millions of light-years, these tiny differences accumulate, potentially producing a cold imprint in the CMB. Mathematically, these models can be tuned to produce a cold spot-sized effect. This is one reason they appear in the literature. They often emerge from attempts to explain multiple CMB anomalies at once. Not just the cold spot, but also the hemispherical asymmetry and large-angle power deficits. But despite their imaginative appeal, such theories face significant scientific challenges. The first limitation is observational constraint. Planck's measurements of the CMB, along with baryon acoustic oscillation data and supernova surveys, strongly support a cosmological constant with W approximately -1 and a little evidence of spatial variation. Dynamical dark energy models require parameters that risk contradicting multiple independent datasets. Any significant spatial variation in dark energy density would likely leave signatures not only in the CMB, but also in large-scale structure, lensing statistics, and the growth of cosmic filaments. So far, observations do not show such signatures. Another limitation is fine-tuning. Modified gravity or varying dark energy models can be constructed to fit the cold spot, but doing so often requires adjustments that affect cosmological predictions elsewhere. When tested against the full suite of observations, cluster counts, weak gravitational lensing, galaxy evolution, many of these models fail. They solve the cold spot by breaking something else. A third issue lies in predictability. The cold spot is a single observed feature in a single universe. A theoretical model gains credibility when it predicts patterns that can be tested independently, but a model built to explain one anomaly risks overfitting. It may describe the cold spot beautifully while lacking broader predictive power. Another scientific concern involves scale. The cold spot spans roughly 5 to 10 degrees on the sky, corresponding to hundreds of millions of light-years. For dark energy variations or modified gravity to operate at such scales, they must be large enough to affect cosmic expansion locally, yet small enough not to violate constraints from the rest of the CMB power spectrum. This balance is difficult. Any significant shift in local expansion dynamics would leave measurable imprints in the CMB's multipole structure or polarization pattern. Planck's high-precision data does not show such distortions. Even the concept of a dark energy void or dark energy bubble faces theoretical hurdles. For instance, regions with different dark energy densities must be connected by transitional boundaries where pressure gradients appear. These boundaries would likely generate additional signatures, such as anisotropic expansion or distortions in redshift distance relations, none of which have been observed. Modified gravity theories face similar constraints. They often predict deviations in gravitational lensing or in the ratio of matter clustering to lensing strength. Again, current observations do not support such deviations strongly enough to endorse these theories as explanations for the cold spot. Still, the idea that dark energy could play a role remains intriguing. The cold spot sits on a scale large enough to hint at physics operating beyond simple Gaussian fluctuations, but small enough that local structures like voids struggle to explain it. This intermediate regime between cosmic structure and cosmic background lies precisely where exotic dark energy models naturally operate. Yet the limitations remain. Despite decades of theoretical development, no dark energy variation or modified gravity framework convincingly explains the cold spot without creating inconsistencies elsewhere. These ideas remain speculative, mathematically possible, but observationally constrained. The cold spot survives these investigations unchanged. A persistent dip in the CMB, tantalizing but stubborn. Exotic explanations involving dark energy or modified gravity expand the imaginative space of cosmology, but they do not settle the mystery. They highlight how little we understand about the cosmic acceleration that shapes the universe, yet they also remind us how tightly observational data constrains our theories. The photons from the cold spot have been travelling since the universe was only 380,000 years old. Their journey has carried them through expanding space, through gravitational potentials, through the silent architecture of the cosmic web. If dark energy had been different in that region, or if gravity behaved differently, those photons would bear the marks. But the evidence so far does not whisper loudly enough to confirm such ideas. The cold spot remains for now, caught between conventional explanations and exotic possibilities. The universe leaves its imprint, but not its reasons. The anomaly sits quietly in the oldest light, neither dismissed nor explained, urging us to look deeper at the forces shaping cosmic expansion. One of the most striking and imaginative explanations for the cold spot comes from the frontier of cosmology. The idea that our universe may be just one bubble in a far larger cosmic landscape. This possibility arises naturally in certain models of cosmic inflation, the brief but extraordinary expansion that occurred fractions of a second after the Big Bang. In some inflationary theories, inflation never ends everywhere at once. Instead, it ends in patches, each of which becomes its own universe, embedded within a vast and ever-expanding multiverse of inflating space. In this picture, our observable cosmos is a bubble universe, and if we are one bubble among many, then collisions between bubbles are not only possible but inevitable across long stretches of cosmic time. If such a collision occurred early enough, before recombination, its imprint could appear in the cosmic microwave background. Among the many proposed signatures of a bubble collision, one of the most discussed is a large, coherent, cold or hot region imprinted onto the CMB sky. The cold spot seems to match some aspects of these predictions. It is large, it is coherent, it stands out against the backdrop of Gaussian fluctuations, and its anomaly is difficult to explain with conventional physics. These features make the idea of a bubble collision an alluring possibility, even if deeply speculative. To understand how such a collision might leave a mark, consider how inflation works in models that produce multiple universes. Inflation is driven by a quantum field, often called the inflaton, that determines how fast space expands. In some theories, the inflaton potential is shaped like an energy landscape with multiple valleys. The field rolls slowly down one part of the potential, driving inflation locally. Eventually, in one region, it falls into a lower energy state, ending inflation there and forming a bubble universe. Meanwhile, in other regions, inflation continues. Different bubbles can form at different times and in different valleys of the potential, each potentially with its own physical constants or configuration of fields. If two bubbles form close enough, or at times and locations where their expanding boundaries intersect, they may collide. In the aftermath, a disturbance propagates through the interior of each bubble. If the collision happens early, before recombination, it can affect the distribution of matter and radiation in the emerging universe. The CMB, being a snapshot of the universe at its infancy, could capture that disturbance as a large-scale temperature anomaly. So what would such a collision look like? Theoretical studies predict several distinct signatures. The most common is a large, roughly circular region, either hotter or colder than average, depending on the exact dynamics of the collision. The boundary of this region might have a characteristic profile or gradient. It might show a central depression surrounded by a ring-like enhancement. Interestingly, this pattern resembles the structure observed in the cold spot, a cold central region with a slightly warmer ring around it. The shape arises because the collision perturbs the density and temperature of the primordial plasma in a way that spreads outward symmetrically from the collision axis. The disturbance compresses or rarefies the plasma, altering the temperature of the radiation that emerges at recombination. These effects are subtle, but in principle detectable. In addition to temperature anomalies, collisions could imprint distinctive polarization patterns. The CMB's polarization is sensitive to velocity flows in the plasma. A collision could generate a radial or azimuthal polarization signal aligned with the center of the affected region. Searches for such patterns have been conducted using wmap and Planck data, though the results remain inconclusive. Another predicted feature is a break in statistical isotropy. A bubble collision breaks the symmetry of the early universe, creating a preferred direction. The cold spot, sitting off-center in the Eridanus direction, indeed suggests a localized departure from perfect symmetry. This does not prove anything, but it adds a layer of intrigue. Inflationary models that produce bubble universes do not just allow such collisions, they expect them. In eternal inflation, the inflating background expands exponentially forever, producing bubbles at an ever-increasing rate. The bubble universes themselves stop inflating internally, but the space between them continues to inflate, stretching them apart. Whether collisions are common depends on the model, but the broader framework allows for them naturally. Some inflation models specifically predict that collisions should leave cold imprints. In scenarios where the colliding bubble has lower vacuum energy, the interaction can drain kinetic energy from the plasma or alter the potential through which photons travel, resulting in a cold region in the CMB. Other models predict hot regions, depending on relative vacuum energies and the collision geometry. The fact that the cold spot is cold does not by itself confirm anything, but neither does it contradict these predictions. It's important to emphasize that the multiverse interpretation is not science fiction. It arises from serious attempts to understand how inflation ends. Certain inflaton potentials, especially those involving plateaus, metastable states, or tunneling events, make the creation of multiple bubble universes mathematically natural. These models are studied in string theory, quantum field theory, and cosmology. Whether they are correct is unknown, but they are not fringe ideas invented to explain the cold spot. The cold spot simply happens to be the kind of feature they might produce. Despite the conceptual elegance, multiverse-based explanations face significant scientific obstacles. One limitation is predictivity. Bubble collisions leave signatures only if they occur within our past light cone and early enough to affect the CMB, but the distribution, timing, and nature of such collisions are model-dependent. Without knowing the precise inflationary potential and multiverse geometry, predictions are broad and difficult to test. Another challenge involves observational constraints. While the cold spot looks vaguely like a bubble collision imprint, it lacks some features predicted by detailed simulations. For instance, the polarization signature expected from a collision has not been convincingly detected. The lack of such evidence weakens the case, though it does not eliminate the possibility. The predicted polarization could be subtle, below current detection thresholds. The scenario also struggles with fine-tuning. For a collision to produce an anomaly of the cold spot scale, the colliding bubble must intersect our observable region at just the right angle and time. Too early, and the signature would be erased. Too late, and it would distort structure in ways that are not observed. The required timing is not impossible, but it is particular. Some inflation models naturally predict cold regions, even without collisions. These models involve features or steps in the inflaton potential that create large-scale anomalies in the primordial power spectrum. Such features could reduce temperature fluctuations on large angular scales, producing regions like the cold spot. But these models often introduce additional degrees of freedom or parameters that complicate the otherwise clean fit of lambda CDM to the rest of the CMB. Adding complexity for the sake of one anomaly is scientifically delicate. The multiverse interpretation, despite these challenges, remains fascinating because it connects the cold spot to profound questions. Why does our universe have the laws it does? Why do physical constants have their observed values? Could other universes exist with different parameters? A bubble collision imprint would be a direct piece of evidence for a reality beyond our cosmic horizon. It would shatter the boundaries of observational cosmology and anchor the multiverse in empirical data. Yet caution dominates the scientific conversation. Cosmologists recognize that extraordinary claims require extraordinary evidence. A single cold patch in the CMB is not enough. It could be random, it could be influenced by a void, it could be the result of subtle systematics we have not yet understood. The multiverse explanation must remain, for now, speculative. Still, the cold spot invites the possibility. It is large enough, coherent enough, and unusual enough to push cosmologists into imaginative territory. If the universe is one bubble in a sea of others, then the CMB could in principle carry scars from those ancient cosmic interactions. The cold spot might be one such scar, a quiet bruise from a collision that shaped our corner of the multiverse long before the first atoms formed. And so the anomaly persists, a trace of something slightly out of place, sitting in the oldest light, hinting at the profound possibility that our universe is not alone. Topological defects belong to one of the most intriguing categories of early universe physics, relics not from galaxies or plasma or conventional matter, but from the fundamental fields that once governed the newborn cosmos. Long before atoms formed, and long before the cosmic microwave background was released, the universe experienced a series of symmetry-breaking events. These events, predicted by high-energy physics, resemble phase transitions, much like water freezing into ice. As the universe cooled, the fields that once held perfect symmetry fractured, choosing different configurations in different regions of space. Where these regions met, mismatches formed. These mismatches are known as topological defects. In particle physics, symmetry breaking occurs when a field that once behaved uniformly takes on different states, leaving behind boundaries or knots in space where the choices of the field collide. These boundaries are not imperfections in matter, they are imperfections in the field that defines the vacuum itself. Depending on the symmetry broken and the shape of the potential, different kinds of defects can appear. Two such possibilities are often discussed in relation to the cold spot: cosmic strings and cosmic textures. Cosmic strings are hypothetical one-dimensional defects, thin, immensely dense filaments formed by mismatches in field values. They would be extremely massive, stretching across large cosmological distances, capable of producing gravitational lensing signatures and discontinuities in the CMB. But cosmic strings produce sharp, line-like features rather than circular temperature spots. Their influence would create sudden temperature jumps and edges, not smooth, round depressions. The cold spot structure, smooth, coherent, centrally focused, does not resemble a cosmic string signature. Thus, cosmic strings, while fascinating and still actively studied, are not strong candidates for explaining the anomaly. Cosmic textures, however, are another matter. Textures arise when the early universe undergoes a type of symmetry breaking that does not stabilize into simple structures. Unlike strings, monopoles, or domain walls, textures are unstable. They form as knots or twists in a field configuration, localized balls of energy created by the mismatch of field orientations. These knots do not remain static. They evolve, unwind, and collapse as the field attempts to relax into a lower energy configuration. It is this collapsing behavior that makes cosmic textures compelling candidates for explaining large-scale CMB anomalies. In a universe with textures, each texture collapse produces a specific imprint on the cosmic microwave background. As the texture collapses, it perturbs the gravitational potential around it. Photons passing through this changing potential experience energy shifts similar in spirit to the ISW effect, but sourced by the dynamics of the texture itself rather than by an evolving void or dark energy variation. If a texture is collapsing toward the time of recombination, the gravitational potential it produces becomes deeper as it contracts. Photons entering this potential may gain energy, but because the potential is changing rapidly, they do not necessarily lose the same amount of energy when exiting. The imbalance produces a temperature feature, a cold or hot region depending on the precise dynamics. The signature of a collapsing texture has been studied through simulations, and intriguingly, its shape often resembles the cold spot, a central region of lower temperature with a clear gradient and sometimes a weak surrounding ring. The circular symmetry also matches well. A collapsing field knot produces a smooth, round perturbation aligned with the center of collapse. This contrasts with Gaussian fluctuations, which typically lack such geometric coherence. In 2007, a team led by Neil Turok proposed the texture explanation in detail, showing that a single collapsing texture could produce a large cold region similar to the one observed. The cold spot's angular size, roughly 5 to 10 degrees, was consistent with the scale a texture might produce if it collapsed at redshift Z approximately 6 or later, meaning well after recombination but early enough to affect CMB photons on their journey. Further support came from statistical fits. When researchers compared the cold spot's profile to models of texture imprints, they found that a texture-based template matched the data slightly better than a simple Gaussian fluctuation template. This was not a definitive result, but it hinted that something non-standard might be at work. However, the texture hypothesis faces challenges. The first issue is abundance. In theories where cosmic textures arise, they do so rarely. The expected number of texture collapses large enough to leave detectable imprints on the CMB is on the order of 1 or 2 across the entire sky. Seeing one is not impossible. Indeed, the cold spot could be exactly such a rare occurrence, but it means the hypothesis must be judged carefully. If textures were more common, they would leave multiple imprints, altering the statistical structure of the CMB. We do not see this. The CMB sky otherwise looks remarkably consistent with Gaussian predictions. Another challenge comes from polarization measurements. A collapsing texture should produce a distinctive polarization pattern around its imprint, especially in the CMB's E-mode polarization. While Planck's polarization maps have limitations at the largest angular scales, no clear texture-like polarization signature has been definitively identified in the direction of the cold spot. This weakens the case. Though it does not eliminate it, the predicted signal is subtle and could be buried in noise. A third difficulty lies in theoretical motivation. Textures emerge from certain symmetry-breaking patterns found in high-energy physics, particularly nonlinear sigma models, but not all theories predict such symmetry breakings. To argue for textures, one must assume specific field dynamics in the very early universe, often involving high symmetries such as SU2 or higher dimensional gauge groups. These models are mathematically elegant but remain speculative. They do not contradict known physics, but they extend beyond what is currently testable in laboratory conditions. There is also a question of amplitude. Simulations show that textures can produce temperature perturbations with amplitudes of tens of microkelvin, sometimes reaching levels comparable to the cold spot. But the precise amplitude depends on the energy scale of the symmetry-breaking event. If the energy scale is too low, the texture produces too weak a signal. If the scale is too high, it produces too strong a signal and risks contradicting other observations. The parameters must be tuned carefully to match the cold spot's depth without creating additional anomalies elsewhere in the CMB. Despite these constraints, the texture hypothesis remains one of the more physically grounded exotic explanations. It does not require dark energy variations, modified gravity, or speculative bubble collisions. It arises naturally in some models of grand unification and early universe field theory, and its predicted CMB signature aligns reasonably well with the cold spot's morphology. Observationally, the case is mixed. Some analyses suggest a texture interpretation improves the statistical fit to the cold spot by a modest but notable margin. Others argue that when accounting for the look elsewhere effect and selection biases, the statistical improvement becomes marginal. Planck's data, while more precise than wmaps, has not decisively ruled out textures, but neither has it offered strong support. What strengthens the texture idea further is its compatibility with the cold spot's central profile. The anomaly has a smooth gradient, a lack of sharp discontinuities, and a circular symmetry that fits naturally with the collapse of a field configuration. Gaussian random fluctuations rarely produce such clean, large-scale structures. Voids produce cooler spots, but typically with shallower profiles. Dark energy variations struggle with observational constraints. Bubble collisions predict certain polarization patterns not yet seen. Textures sit in the middle, exotic but not extravagant. They require new physics, but physics that many theories already anticipate. They do not solve every aspect of the anomaly, but they do offer a coherent mechanism capable of producing the right scale, shape, and depth of the cold spot's core. Still, the evidence is insufficient. No polarization signature, no secondary imprints, no accompanying anomalies from other texture events. If the cold spot were caused by a cosmic texture, it might be the only such event large enough to leave a visible mark. This is possible, but tightly constrained. Ultimately, the texture hypothesis embodies a profound possibility that the cold spot is a fossil not of plasma physics or cosmic structure, but of field dynamics from the earliest fractions of a second after the Big Bang. It would be a relic from energies far beyond anything accessible to particle accelerators, a whisper from a time when the universe's fundamental symmetries were shattering into the forms we observe today. Whether this whisper is real or merely an enticing coincidence remains unresolved. The cold spot continues to sit at the intersection of theory and observation, inviting explanations from both established and speculative corners of cosmology. Textures offer one of the most mathematically precise and physically grounded exotic interpretations. But like everything else about the cold spot, they leave the mystery partly intact, partly illuminated, and wholly compelling. The debate over the cold spot sits at a crossroads between scientific caution and cosmic curiosity. For nearly 2 decades, studies have oscillated between two broad interpretations: that the anomaly is an unremarkable statistical coincidence, or that it whispers something deeper about the early universe, perhaps even physics beyond the standard cosmological model. The argument is not simply about a cold patch of sky. It is about how cosmologists interpret rare events, how they balance extraordinary data against extraordinary claims, and how they use statistics to distinguish meaningful signals from the natural oddities produced by randomness. The first step in this debate involves statistical methodology. The cosmic microwave background is inherently a random field, seeded by quantum fluctuations and shaped by inflation. Because of this, cosmologists must rely on probabilistic tools to determine whether a particular feature is unusual. Gaussian random field theory provides the baseline. It predicts the amplitude and distribution of temperature fluctuations across different angular scales. The CMB's power spectrum, its distribution of fluctuations by size, matches these predictions remarkably well. To evaluate anomalies like the cold spot, researchers generate vast ensembles of simulated CMB maps based on the lambda CDM parameters. These simulated universes follow the same statistical rules as the real one, but differ in specific arrangements of hot and cold regions. By comparing the cold spot to these simulations, cosmologists estimate the likelihood of a feature of its magnitude appearing by chance. Depending on the analysis, the probability ranges from roughly 1% to perhaps 2 to 5%, though the exact value depends on definitions of depth, radius, and how the look elsewhere effect is handled. The look elsewhere effect is crucial. If you scan the entire sky for unusual features, the mere act of searching increases the probability you will find something statistically significant. This is not a flaw. It is an inherent property of large datasets. In a field of billions of values, outliers will appear naturally. The cold spot may simply be that outlier. Because probabilities of around 1 to 2% are not astronomically small, many skeptics argue the cold spot requires no exotic interpretation. They point out that the CMB contains several large-scale anomalies, low power at large angular scales, alignments in low multipoles, hemispherical asymmetries, but that each of these falls near the threshold of statistical significance. None clearly violates the standard model. Together, they may look suspicious, but the combined significance is difficult to evaluate without introducing biases. Skeptics emphasize that anomaly hunting can mislead cosmology. The CMB is one of the richest datasets in all of science. If researchers test enough hypotheses, explore enough subsets of the sky, or define anomalies retrospectively, patterns can emerge that reflect nothing more than statistical fluctuations. It is the same principle behind seeing faces in clouds. The human brain excels at finding structure, even when none is intended. In this view, the cold spot is interesting, but not alarming. It is one of the rare but expected deviations in a vast statistical field. Its properties lie within the extreme tails of Gaussian predictions, but do not exceed them. And because the rest of the CMB fits lambda CDM so superbly, down to sub% precision on many parameters, throwing out the model because of one unusual feature would be scientifically reckless. But proponents of a physical explanation counter with equal energy. They argue that the cold spot is too large, too coherent, and too deep compared to typical fluctuations. They highlight that the anomaly appears across multiple frequencies and multiple spacecraft, eliminating the possibility of foreground contamination or instrumental noise. They point out that the cold spot's radial profile contains a characteristic central depression and a surrounding ring, something not easily produced by Gaussian randomness. And they emphasize that certain inflationary models or topological defect scenarios naturally predict anomalies of this scale. Studies from 2005 to 2023 reflect this tug of war. Early analyses in the mid-2000s leaned toward the anomaly being significant, especially after wavelet-based methods enhanced its visibility. These techniques, such as the spherical Mexican hat wavelet, amplify localized structures and allow clearer detection of deviations from Gaussianity. Using these tools, researchers originally claimed the cold spot was inconsistent with random fluctuations at the 3 to 4 sigma level. Such numbers fueled speculation and opened the door to exotic explanations. However, follow-up analyses questioned the methodology. Wavelets emphasize certain shapes and scales, potentially biasing the significance estimates. When researchers used alternative statistical tools, such as Minkowski functionals, multipole decompositions, or real space variance maps, the anomaly's significance dropped. The probability of a cold spot-like feature appearing in the lambda CDM universe rose modestly. Some methods placed the probability above 2%, others below. But none ruled out the random fluctuation hypothesis decisively. By the early 2000s, the debate matured. Studies compared the cold spot to large-scale structure surveys, searching for corresponding voids or galaxy deficits. Some found hints of underdensity in the Eridanus region. Others found the void insufficient to explain the anomaly. These mixed results reinforced the idea that the cold spot could represent a convergence of factors, partially random, partially physical. Then came Planck's 2013, 2015 and 2018 data releases provided the most detailed CMB measurements ever collected. The mission's analysis teams treated the cold spot with scientific neutrality. They neither dismissed it nor embraced exotic explanations. Instead, they evaluated its significance rigorously. Their official stance was cautious. The cold spot is an unusual but statistically permissible feature of lambda CDM. Planck confirmed the anomaly's existence with high confidence, but found no decisive evidence of non-Gaussianity associated with it. Their polarization data, which could have offered key clues, contained too much large-scale noise to settle the matter. While some analyses of Planck data favoured the texture hypothesis by a small margin, others did not. No model provided a dramatically better fit than standard cosmology. Planck's official assessment can be summarised simply: the cold spot is interesting, but not compelling enough to imply new physics. This conservative conclusion reflects cosmology's broader methodological caution. The field relies on statistical inference drawn from a single universe. This means that false positives can be discovered easily. Every anomaly must be evaluated contextually, not in isolation. Cosmologists often cite the cautionary lesson of earlier claimed anomalies, such as large-scale alignments in quasar polarization or the so-called axis of evil, that later faded in significance or were reinterpreted as statistical curiosities, yet anomaly hunting remains valuable. Some of the greatest breakthroughs in physics emerged from unexpected irregularities. The orbit of Mercury deviated slightly from Newtonian predictions, helping to reveal general relativity. The ultraviolet catastrophe in blackbody radiation exposed the need for quantum mechanics. Fluctuations in galactic rotation curves pointed toward dark matter. In each case, anomalies were the starting point for revolutionary shifts in understanding. This duality, anomalies as potential pitfalls or as gateways to discovery, is central to the cold spot debate. On one hand, overinterpreting rare fluctuations risks drawing unwarranted conclusions. On the other hand, ignoring persistent irregularities risks missing the very clues that point toward new physics. The cold spot sits precisely in this tension, refusing to align neatly with either side. Some researchers argue that the anomaly's mere existence encourages continued exploration, even if it ultimately proves to be a statistical accident. Investigating it forces cosmologists to refine tools, test inflation models, improve void catalogues, and deepen understanding of cosmic structure and early universe physics. Anomalies, even mundane ones, sharpen theories. Others argue that the cold spot, considered alongside other large-scale anomalies, may point toward a subtle deficiency in lambda CDM. Perhaps the model's parameters capture the universe's average behaviour well, but miss rare processes or initial conditions that influence the largest scales. From 2005 to 2023, the cold spot has weathered extensive scrutiny. Dozens of studies analysed it through wavelets, polarization maps, galaxy surveys, dark energy models, modified gravity frameworks, texture simulations, bubble collision templates, and statistical reconstructions of primordial fluctuations. Each approach contributed a piece to the debate, yet none delivered a definitive conclusion. This persistence is what gives the cold spot its staying power. Unlike more fragile anomalies that fade with better data, the cold spot remains. Its significance may have softened, but it has not disappeared. It is an anomaly that refuses to resolve into either triviality or revelation. The debate continues, not because the cold spot demands new physics, but because it occupies a rare middle ground. It is improbable but not impossible, suggestive but not decisive, visible but not definitive. It is neither mere coincidence nor clear cosmic clue, yet it could be either. The oldest observable light in the universe was never meant to be perfect. The cosmic microwave background is often described as uniform, smooth, even serene. But beneath that calm exterior lies a subtle, unavoidable truth. In every direction we look, the universe carries the memory of tiny imperfections. These small irregularities are the fingerprints of conditions that once shaped everything. Without them, galaxies would never have formed, stars would never have ignited, and life would never have emerged. In a sense, the universe needed its imperfections. The cold spot, whatever its origin may be, is a reminder that even in the most ancient cosmic light, the universe leaves room for irregularity. Finding an anomaly in the CMB is like discovering a ripple in an otherwise tranquil pond, a ripple that has persisted for nearly 14 billion years. It reflects the idea that randomness is not a flaw, but a fundamental part of cosmic history. The small temperature fluctuations scattered across the sky show where matter was a little denser or thinner, where the seeds of cosmic structure first took root. These fluctuations are tiny, just microkelvin deviations from the mean, yet they eventually determined the distribution of galaxies across billions of light years. The cold spot, more pronounced than most, becomes a symbol of this cosmic randomness writ large. It invites reflection on what it means for the universe to have quirks and irregularities. Not everything aligns neatly with expectations. Even in a model as successful as lambda CDM, anomalies survive. The universe, despite obeying laws of physics with remarkable consistency, also preserves the imprint of chance. The outcome of a quantum fluctuation stretched across unimaginable distances, or perhaps an event we do not yet fully understand. This sense of randomness does not diminish the universe's elegance, it enhances it. Perfection leaves no room for stories. Irregularity is where narratives begin. The cold spot represents a place where the universe did something slightly different, leaving behind a quiet puzzle embedded in the background light. Whether it is a random fluctuation, the shadow of a vast supervoid, a topological texture, or an imprint from a cosmic collision, its mere presence adds depth to our picture of the cosmos. Beyond the randomness lies another philosophical dimension. The cold spot hints at the boundaries of what we can observe. The CMB marks the limit of our vision, the cosmic horizon beyond which no light can reach us. It is not the edge of the universe, but the edge of the observable universe. Beyond that horizon, there may be regions of space forever out of reach, a bubble universe, a different inflationary domain, or simply more of the same cosmic web stretching infinitely farther. The truth lies beyond what photons can show us. In this context, the cold spot becomes a kind of shadow cast from a realm we cannot see. If it were caused by something beyond the surface of last scattering, a feature imprinted by early inflation or by another universe's brush against our own, then the anomaly would represent the faintest contact with realities outside our cosmic horizon. Even if the cold spot turns out to be a statistical fluctuation, the possibility that it might reflect deeper physics reminds us how thin the boundary of observability truly is. Our understanding of the universe is shaped not only by what we see, but by what we cannot see. The CMB is both a map and a limit. It marks the earliest moment accessible to observation, yet behind its uniform glow lies the unobservable history of fields, energies, and structures that predate recombination. The cold spot draws our attention to these hidden epochs. If it carries the imprint of pre-recombination physics, then it becomes a rare window, even if narrow, into times otherwise sealed behind the fog of the primordial plasma. But perhaps the most important philosophical aspect of the cold spot is what it reveals about human curiosity. Anomalies spark questions. They create tension between expectation and observation. They push us to refine theories, test new ideas, and look for deeper explanations. The cold spot could have been dismissed as an uninteresting dip in temperature, yet it has inspired research across cosmology, astrophysics, and fundamental physics for nearly 20 years. Entire studies, surveys, and theoretical frameworks have been developed in response to it. There is something uniquely human about this response. We are drawn naturally to the unusual, the asymmetric, the thing that stands out. A smooth sky is elegant, but a sky with a single unexpected feature becomes compelling. Curiosity thrives on difference. The cold spot reminds us that science does not advance only through confirmations, but also through tensions and contradictions. Questions shape our understanding as much as answers do. This longing to know more, paired with the humility of uncertainty, sits at the core of cosmology. The universe provides us with a single, unrepeatable dataset. We cannot run experiments on different universes. We cannot rewind cosmic evolution. We observe what is given, and from those observations, we build our understanding. The cold spot tests that understanding. It asks whether we should accept randomness, search for deeper structure, or consider new physics. It offers no definitive answer, only the challenge of interpretation. In a broader sense, the anomaly echoes the way humans interact with the unknown. We live in a universe vast enough to humble us, yet comprehensible enough to invite investigation. The cold spot is a perfect embodiment of that duality, a feature large enough to catch our attention, yet subtle enough to resist explanation, an imprint of ancient processes, yet one that speaks directly to modern curiosity. The philosophy of the cold spot lies not in its temperature, but in its persistence. It persists in the data, in debates, in theoretical reflections, in the imagination of scientists. It persists as a reminder that even the universe's calmest, most ancient light hides secrets. Imperfections are not flaws, they are signals, and even when those signals cannot be fully understood, they guide us toward deeper questions. Whether the cold spot is random or meaningful, ordinary or extraordinary, it has already served its purpose. It has encouraged cosmologists to examine how we interpret anomalies, how we balance skepticism with openness, and how we navigate the narrow path between statistical noise and physical insight. It has strengthened tools, sharpened thinking, and expanded the landscape of possible explanations. In the end, the cold spot stands as both a scientific puzzle and a philosophical mirror. It reflects our desire to understand the universe fully and our recognition that the cosmos will always exceed our complete grasp. It reminds us that the deepest truths often emerge from the smallest deviations, and it shows that even in the oldest light, a nearly perfect relic of cosmic origin, there is room for nuance, subtlety, and wonder. The oldest light of the universe has a way of quieting everything else. After wandering through theories, statistics, cosmic structures, and the deep imagination required to consider multiverses and ancient topological remnants, the cold spot remains where it has always been, an unmoving whisper in the microwave afterglow. No matter how complex the explanations become, no matter how sophisticated the analysis grows, that patch of sky sits in the calm maps with the same calm, faint depression in temperature. It does not change. Only our understanding circles around it. Reflecting on the cold spot is like returning to a familiar vantage point after exploring distant paths. Each trail, the void hypothesis, dark energy variations, textures, statistical arguments, bubble collisions, extends into different regions of cosmological thinking. Yet they all reconnect here, at this quiet imperfection in the universe's first visible light. Whether the anomaly is a clue or a coincidence, it holds a rare place in the story of the cosmos, an unresolved detail that resists easy categorization. There is something compelling about a universe that reveals so much and yet leaves room for mystery. The CMB is one of the most precisely measured phenomena in science. We know its temperature to extraordinary accuracy. We understand its spectrum. Its tiny ripples have allowed cosmologists to determine the universe's age, composition, geometry, and evolution. It has constrained dark matter, dark energy, neutrino properties, inflationary models, curvature, and countless other aspects of cosmology. And still, within this triumph of understanding, a single cold patch remains uncertain. Part of the cold spot's quiet beauty is its ambiguity. It sits at the edge of knowledge, in a space where data ends and interpretation begins. We know enough to recognize its persistence, but not enough to assign it a definitive cause. It is neither obviously physical nor easily dismissed as chance. It inhabits a thin line, one that makes scientific inquiry both humbling and exhilarating. Human curiosity gravitates toward such boundaries. We are drawn to questions that resist closure. The cold spot invites reflection on the nature of scientific progress, that not every question resolves neatly, that not every anomaly demands an explanation, and that some phenomena may remain open, encouraging us to explore new methods, refine models, and broaden our conceptual horizons. The cold spot is not a failure of cosmology, it is a reminder of the discipline's vitality. Will we ever truly solve it? Possibly. New galaxy surveys, deeper sky mappings, improved polarization data, and future CMB missions may reveal more about the structures along the line of sight or uncover subtle signatures consistent with one hypothesis over another. More precise simulations could refine statistical expectations, yet it is equally possible that the cold spot will remain inconclusive, a permanent feature of the CMB whose origins lie hidden behind cosmic variance, inaccessible in a universe we can observe only once. And there is a certain beauty in that possibility. Unanswered questions do not diminish our understanding, they deepen it. They show that the universe is not a closed book, but a dynamic landscape with corners still shrouded in quiet uncertainty. Mystery is not merely the absence of answers, it is an active component of discovery. It encourages patience, creativity, and humility. The cold spot invites us to imagine processes that lie beyond current theories, to entertain possibilities from the subtle to the extraordinary, and to appreciate the tension between chance and meaning. It reminds us that the cosmos is not obligated to make every one of its details transparent. Some aspects may remain hints of deeper truths, accessible only through indirect signs or incomplete data. And yet, despite the unanswered questions, there is a strange comfort in returning to the CMB itself. The oldest light continues to wash over the sky, uniform and gentle, carrying the imprint of the universe as it transitioned from opaque to transparent. It connects us to a moment long before galaxies formed, long before stars ignited, long before anything recognizable as structure emerged. The cold spot is simply one feature within that vast ancient landscape, an imprint preserved across billions of years, quietly holding its place. As the reflection returns to the present, the strangeness of the anomaly softens. The cold spot becomes less of a puzzle to solve and more of a reminder of the cosmos's scale and subtlety. It reveals that even in a universe governed by consistent laws, small deviations can persist, hinting at stories that may never be fully told. It shows how the smallest irregularities in the CMB correspond to enormous structures, and how a single unusual dip in temperature can inspire decades of research. Standing here, far removed from recombination and surrounded by modern light rather than ancient radiation, the cold spot feels less like a problem and more like a window into the early cosmos, into the limits of observation, and into the relationship between knowledge and uncertainty. Even if it remains unexplained, its place in scientific thought is secure, and its presence offers a gentle reminder that wonder often grows in the spaces where certainty thins. The oldest light fades slowly from the mind's eye. The vast microwave glow recedes, leaving the quiet of the present moment. The cold spot remains in the sky, unchanged, unbothered by interpretation, waiting patiently for whatever future insights may come. For now, it rests as it always has, a faint depression in the cosmic afterglow, a soft reminder of randomness, possibility, and the enduring human desire to understand the universe in all its detail, even the parts that refuse to resolve completely.